Up next, I'm going to give a quick overview of assignment 2, although hopefully you've already seen this and gone over this. I've even gotten a few questions on the discussion forum already, which I'm really happy about. This assignment is all math, all asymptotic notation. Different questions have different rules, and you'll only be able to get marks by following those rules. They're detailed in this global instructions header. And then the questions are sort of grouped together such that there's one set of questions for the big notations, like big O and big omega. Big theta is separate. It's in its own group. So one group for big theta, like I said, and another for little o and little omega. Question 2 is a bit of a curveball because it doesn't look like anything we've done in class. You'll really have to get the gears turning in your brain to figure out a value of n that works for negating the definition of big O. This square isn't just for emphasis. It links to the Wikipedia article on the function you'll need to do this. Floor and ceiling functions basically round up or round down, and they're really useful in theoretical computer science in general, because a lot of the time our analysis of algorithms and the functions we use to describe their properties deal with real numbers, but computers themselves deal with integers. They can attempt to approximate real numbers using floats, but that often ends badly. So we often use the floor and ceiling functions to sort of convert from real numbers to integers. And here, hint, hint, you'll use that floor and ceiling function differently from how I just described, but you'll use it to convert from a real number to an integer that lets you apply something you learned on the very first class, the definition of an even number. When I was making this, these memes popped into my head, and I'm frankly kind of impressed with myself that I still have them saved. All my undergrad stuff is weirdly well preserved. All right, and then in questions 5 and 6, you stop using the definitions. All the previous ones use the definitions. And you use the asymptotic notation facts found in the readings. Question 5b is going to be relatively straightforward, but super tedious. So sorry in advance. I could maybe kind of sort of justify it as it being a neat example of small, basic, straightforward facts being able to come together to make a sort of complex structure. And then question 6 is the reason I put that little clarification in the announcement. You won't have to prove new asymptotic properties based on definitions until the last assignment in a bonus question. But this right here is a question about proving asymptotic properties from other known properties. The property in question is that if f is in big theta of h and g is in big theta of h, so f and g grow roughly the same as a third function, then the sum of f and g grows at that same rate. Adding them doesn't change anything. And then 6b uses that fact, and you can use it without proof, but if you're really clever, you could do it without using part A at all. And yeah, you'll still get full marks for that. And limits. Highly recommend going for this bonus. I probably could have included it as a mandatory question, but I wanted to be nice. These limits are at about the difficulty level of a limit that you would see in Math 1500. Intro calculus for students who aren't in a mathematically focused discipline. I think that's the term. So if you're still familiar with the calculus class, that was probably a prerequisite for this, maybe? Probably. If you're still familiar with intro calculus, you should do these. 3 relatively easy marks. Okay, well that's probably everything besides a lecture that I was going to go over. Yeah. Let's lecture. We're going to talk about something completely different now. I would say we're done with theory, but that's not quite true. We still have some concepts that don't directly translate to code that you're writing, but this theory is a lot more grounded in computer science and, dare I say, more useful in a real-world job. We're going to learn about abstract data types. Oh, yeah?
Sorry, going back to the assignment, does that mean that there's 4 possible bonus marks you can get on the assignment?
Yeah.
Oh,
Oh yeah, the thing about submitting it electronically for proofs, that'll apply to every assignment. So yeah, we're going to talk about abstract data types, sort of forming the backbone of all data structure lessons we're going to talk about in this entire course, and will be something that you'll need to remember on the job to make good implementation decisions when writing code. You probably won't need to remember the name abstract data type, but I guarantee you're going to be thinking about this sort of concept. An abstract data type, or ADT, consists of a collection of data, together with the structure, organization, and properties of that data, and the operations that can be performed with that data. So what the user can do to examine or manipulate it. Like any definition, it's probably not that meaningful at this point, but the examples we'll see will sort of retroactively motivate what's in the definition. If you've ever worked with interfaces before in Java, an abstract data type is basically the idea behind an interface. It's a bit different, but the ideas are very similar, and when we get down to coding stuff, we're basically going to use interfaces to represent abstract data types. Something that will be very useful to keep in mind, probably for this week's quiz, is the difference between a data structure and an ADT. This is something that I hope will become clear throughout the lecture, but they're not the same thing. An ADT is sort of the idea of a data structure. So what stuff it contains and what you can do with it. Whereas a data structure is the concrete implementation of an ADT, the actual code used to put it into a program. I was trying to think of examples that are sort of real-world grounded, and it's kind of tough to. This is really a computery idea, but you could think of physical tools as having a sort of relationship between interface and implementation similar to this. Like, if you have a shovel, the interface, or the abstract data type, would be that it has a handle and a thing you could use to dig. And then its implementation would be the materials you use to create it, the exact specifications of its parts. It's not the best metaphor or comparison I've ever thought of, but it might help. This connects to something that you'll be learning again and again throughout your degree, which is data organization and abstraction. So at the lowest level, there are bits, bytes, words, and addresses, the stuff that's actually happening on the electronics of a computer. And those are worth knowing about, but in pretty much all cases, we abstract those details away and focus on some higher level constructs that are defined in terms of the previous level. So taking bits, bytes, words, and addresses for granted, you can then start worrying about arrays, classes, and pointers. So the stuff we're going to study is one level of abstraction above that. You already know how to use arrays, classes, and pointers. You have a general idea of how they work. Some of the nitty-gritty details of them are hidden from you, so you don't have to worry about them. And then once you have all those things set, you can worry about ADTs. Things like lists, tables, stacks, and queues are usually provided in libraries so that you can use them. In this course, we're going to learn about how they're implemented, which will basically make you really good at using them in the real world, which is sort of the final level of abstraction on this list. You're going to learn about ADTs and how to implement them in this course, and then in your job, you're going to use that knowledge to make applications using ADTs. This hierarchy is definitely not comprehensive. Like, you could go even lower level than bits and bytes, become an electrical engineer. And also above application-specific application-specific stuff, there are a million other layers of abstraction you could go into in the real world. Weird stuff like the cloud and software engineering. Ooh. So let's look at our first example of an ADT. Although I guess we've already seen a couple. Lists, tables, stacks, queues. I'm going to assume you know what a list is. It's kind of the simplest possible ADT. It holds data and then you can add or remove data. Cool. And then tables, stacks, and queues. You may have seen before in classes like Comp 1020, but I'm not going to assume that much prior knowledge in them. I'm not going to have any readings to defer to either. Those ADTs have more specific interfaces, and they end up being less capable than a regular old list, but their restrictions end up making them useful to sort of reduce the amount of possible bugs in a specific application. We're going to learn about all of these. But first, we have a sort of contrived example that shows what an ADT is and exhibits some properties of them. So let's say I'm making an ADT, me, like I'm doing this. I'm making an ADT to represent a course that I'm teaching. Maybe I want to make an application that manages courses and stuff, like making Aurora 3 or something. And I'm sitting down, I just made a new file, class.java. Oh geez, that's a confusing name. Course.java? Yeah, that's probably better. Class course. So as I'm writing the class for a course, I need to think about what data it needs to, or data I need to organize using this class or data structure, and what actions it might take. So each student enrolled in the course has different properties like a name, student number, student ID, email, their grades in the course I might also keep track of. The course has assignments, grading scheme, size. You can kind of start thinking in the background how each of these will be actually stored in a program. Like name is obviously going to be a string, student number is going to be probably an integer. Storing grades gets more complicated, but it's not actually that important for now. We're focusing on what data I need to organize and the actions I might want to take. Speaking of actions, some actions that might be in this ADT are enrolling or unenrolling a student, looking up a student's grade, calculating a student's grade, getting the class size, stuff like that. As part of the separation between ADTs and data structures that you'll be gradually absorbing through this part of the course, it's worth making a comparison that the actions that you want to take are pretty much always the methods of the class that implements your ADT, and then the data that I need to organize. I can definitely think of what this should be. You probably can too, but I'm struggling to remember the name. It's either variables, fields, properties. I'm just going to say variables because it's sort of a generalization of fields and properties, and I don't want to choose the wrong one. So again, the data you need to organize and the actions you want to take are part of the ADT, and then you'll eventually implement the ADT by turning that data into variables and actions into methods. And here's a usage example. We have a student in the course, KitKat, adorable, and you could see stuff that's being used, like the ADT is being used in the program. We have that we're using the enroll action to store the data KitKat, and then we're using some of its methods, basically just getters. We don't know how exactly they work, but we know what they're doing. Like, what's a good example of this? I guess get assessment grade is a decent example. Its interface, the idea behind it, is really easy to understand. You give it a student and an assignment name, and it gives you that student's grade in that assignment. But how it's working is completely mysterious. How are assignments stored? how are the grades calculated? Does it like store the rubric and the results for each question and calculate it all in that method? Or does it store the assignment grades directly and just look them up in a table or something? We don't know. And that's important. Sort of getting ahead of myself. I'll finish up this stuff on this slide. So this usage example hides many of the details of what exactly the ADT is doing. Like when we enroll KitKat, we don't know if it's like adding the student to an array, adding it to a linked list, whether that list is sorted, whether it's even using an array or linked list. It's just never specified. And we don't have to think about it. Just add a student and it is added. Wahoo. We also don't know what algorithms the methods are using. Like if you're searching for a student, is it using linear search or binary search? That choice would be affected by the choice of data structure for storing students, which we also don't know. So yeah, stuff like that. We don't know how this works. And that's good. A big reason why we care about any of this stuff, instead of like just saying, I don't know, make a class, like it's simple. We care about ADTs for the sake of information hiding. When you're implementing an ADT, like if you're creating the Comp 2140 class, you need to make it so anyone else using the code can't know how the data is stored and how the operations are implemented. And once you establish that information hiding, that has two main benefits. One is that when the user is not allowed to know the implementation details, they don't have to worry about the implementation details. Like, say we're storing student names using some esoteric data structure. There's one that you might learn about in third year called a skip list that starts with a linked list, but then has some kind of cool quirks to its structure to make it faster. Yeah, say the programmer behind this is super advanced and uses a skip list, but this code is being made for other programmers who might not know that. Well, if you did your information hiding correctly, the person who is using the ADT, like writing the code on this slide, doesn't need to know how to use a skip list. They just need to know how to call your enroll method. So even if the implementation of the ADT is very complicated, hiding that fact from other programmers allows you to create a simple interface for them to use. Another benefit to this is being able to make changes to your ADTs without messing up other people's code. You'll learn more about this in courses like software engineering and Comp 2160, if that's still around. I know it's going away, maybe this term or the previous. But it's being replaced by something that's probably still going to talk about this stuff. I'll still give a quick overview here. So say you're working at a company and you've made some data structure that your coworkers are using, and you're using an array to store stuff, but then you realize that a linked list would work far better. Maybe there's some memory constraints that you didn't discover until recently. I don't know. If you did your information hiding badly, then the people using your code might be interacting directly with your array. And so changing your data structure to use a linked list would break it. Everyone using your code would have to change their code to accommodate your changes. But if you're doing information hiding correctly, the way that other people use your code will have nothing to do with the specific data structure used to store it. Like, I don't know, maybe you're using, or maybe you're in the company making Aurora 3, and you decide to make it so the way to add a student to the course is .enroll instead of going like, don't write this down. It's going to be bad, and I'm going to erase it. .students num students plus plus. Whatever. Doing this incrementing thing inside of an array index is really dangerous. Please don't do this. Just increment the array index after you're done using it. In this case, I actually have just one line to work with. But in the real world, when you're writing code, you're going to have way more lines than this, so please just put it on a separate line. I'm going on a massive tangent in a tangent. I'm just going to fix up this, or finish this one. So the line I just wrote is an example that you could pretty realistically imagine could be there instead of that line comp2140.enroll kitkat. In this case, information is not hidden. The class actually directly exposes the array that it's using to store students. And people using that class are expected to interface with it directly. So if you change this class to use a linked list instead of an array, this line would no longer compile. But if you've hidden the information correctly, then this will continue working. The people using your code won't even realize that anything's changed. They'll be happy. Is this useful? I'm going to erase it because it doesn't really have any context on its own. Will be useful for anyone reviewing video, though. So I hope those rants illustrated the point. When you're implementing an ADT, you should hide the specifics of how it works. I've been throwing the word interface around, but it might not be clear exactly what that means. So an ADT's operations, which is what I'm referring to when I say interface, sort of serve as a contract between the ADT and the user. It's an agreement of what the operations are and what they do. So for example, unenroll student removes the given student from the course and doesn't affect any other student's data. So that you could think of is an agreement, or you can think of that as an agreement between whoever's writing the ADT or whoever's writing the class that represents that ADT and whoever is using that class. If unenroll just didn't remove the student, that would be breaking the contract. If unenroll also affected other students' data, that would also be breaking the contract. The ADT's implementation has to follow the details specified by the ADT itself. And then the contract goes both ways. That first bit was a responsibility on the part of the person writing the ADT. And now, on the side of the person using it, the user must only use the operations supplied by the interface. So maybe you know that the student's data is stored in an array, and you're using that class shown earlier. You should still only use getStudent to retrieve the student's record, and not try to access the array directly. Remember what I said earlier about being able to easily change implementation details? On the user's side, even if you know how it works, you shouldn't take advantage of those details in case they change later. Oh yeah, this slide is just what I was talking about, except this is a different example, worth going over multiple examples. Instead of arrays versus linked lists, this uses a data structure that will be taught later in the course, but you might have heard of, a hash table. So again, you'll learn about hash tables later. I won't go into very much detail about them right now, but they have the very cool property that insertions and sorts are constant time. They have like a million other trade-offs that you have to worry about, but the fact that you can insert elements into them and search for any specific element basically instantly is a huge advantage. So yeah, suppose you've been storing student records in an unsorted array, but this makes it so enroll and unenroll, their implementations are really clunky. Unenroll probably has to loop through the entire array to find the student it wants to unenroll, and maybe even like move other students. Oh wait, no, it's a sorted array. Whatever. I guess the point that I interrupted myself on still stands. If you're doing an unenroll method on a sorted array, you could search for the student you're deleting pretty quickly, but then you'll be left with an empty space in an array, and you'll have to shift every element to the side to make sure that there are no gaps in the array. Exhausting. So you find that this makes enroll and unenroll awkward. You get a little further into Comp 2140 and realize that a hash table is actually a much better data structure for this. So you change it. The internals of your class, like its private methods, have probably changed a lot. They might be completely unrecognizable. But since the outcomes of those operations remain the same, enroll still adds a student and unenroll still removes a student, you preserve the contract, and assuming both sides have been following it, any code that uses that ADT is unaffected. So this is going into a bit more technical stuff. All the slides before this are sort of what I meant by saying that we're not quite done with theory in the course. All this stuff about ADTs, contracts, information hiding, that's theory. Where were we? it doesn't apply to any specific programming language, but it's ideas that you're going to keep in mind regardless of what specific tools you're using. Now let's talk about some specific tools you might be using. When you're applying these ideas in Java specifically, you're going to use an interface to represent the details of the ADT. Like I sort of said earlier, an interface is like an ADT, except not quite. An interface is just a list of method signatures, so what the methods take as parameters and what they return, which is pretty much equivalent to the actions that an ADT might take, or an ADT, the actions that the user might take on an ADT. Interfaces, however, don't have a real equivalent to the data you need to organize part, although you might end up representing that implicitly just with return types and parameter types. So an interface is kind of sort of like an ADT, but not quite. I should mention something else, although I've kind of been alluding to this. ADTs are a purely theoretical thing. They don't exist in your code. You will never create something on a computer, point to it, and say, this is my ADT. At least you'll never create something in code that is exactly your ADT. An ADT is just the idea that gets implemented in code. Yeah, I don't think this stuff or the rest of the stuff in this slide is too relevant. All this stuff about courses being required to implement comp sci course interfaces, that isn't representative of any real life thing. This is purely for example. But we have method signatures, enroll and unenroll, and no specification of how they work. That's what an interface provides you. So when you're implementing an ADT to make an actual object that does the stuff that the ADT describes, you would implement its interface. In this case, making Comp 2140 class that implements comp sci course interface. We would write specific implementations of enroll and unenroll. It's kind of hard to talk about these without any actual examples of ADTs. We named some, lists, stack, queue, table, but the idea of interface versus implementation will be clearer once we actually start looking at ADTs that real people use. Yeah, I think I'm just repeating myself a bunch. When you implement an ADT, you write code that does what the ADT is describing. And more specifically, you're going to choose a data structure and write algorithms that carry out those operations. Java specific again, you're going to use the keyword implements to implement the interface. And that makes it so Java enforces, using the compiler, that your class will use all the methods that are specified in the interface. Okay, this is sort of getting back to better stuff. By the way, we've still got about 20 minutes, and as nice as it would be to let everyone out early, I think I'm going to still get a head start on the next lecture so that the quiz this week doesn't eat into content too much. Yeah, we can easily see why it would be useful to get a little bit ahead of schedule in this course, and given the tight timeline, how it would be catastrophic to fall behind. Yeah?
The quiz, is that on Thursday or is that being pushed to Friday?
Oh, good question. So everything in this week is pushed a bit. The quiz will be on Friday, and it will cover everything up to and including Thursday's class. So I think, anyway, this slide is pretty important. You almost certainly will, at some point in this course, get a bit confused about whether something is an ADT or a data structure. And to tell them apart, a good question to ask is whether there are multiple ways to implement it, so multiple choices that you can make behind the scenes that give rise to the exact same functionality, such that anyone using the class that you make wouldn't be able to tell them apart. If there are behind the scenes choices you could make, you're probably talking about an ADT. If nothing is really behind the scenes, if choices between things like arrays versus linked lists actually matter, then you're probably talking about a data structure. These examples are a bit weird because we haven't talked about graphs nor trees in this course. Depending on the program you're in, like there are some differences between the prerequisites for stats versus engineering versus comp sci. You might have never seen a graph or a tree. We're going to talk about them later in the course, but at this moment, I'm not really sure how to handle them. I think I'll talk about them in a way that will make sense if you've talked about them in a previous course. So a graph, as you may or may not know, has vertices and it has edges, and that's pretty much all you need to know about, or that pretty much describes what graphs are. And say you're making a class in a program that represents a graph. You can't exactly just write array vertex vertices. You have to get a bit more specific. And at the very end of the course, we're going to talk about two ways to implement graphs. Basically, there's two main ways. One of them uses a bunch of linked lists, and the other uses a multi-dimensional array. Don't worry if you're not following. This will be the focus of an actual lecture much later. But the important thing to note here is that when you think of a graph, you're not really thinking of any actual code. It's just a general description of what the object looks like and does. You have to make some choices behind the scenes in order to actually make code for it. So it's an ADT. I'm going to skip trees because it would have pretty much the exact same description as a graph. But an array and a linked list, those are both much more straightforward to implement. If I tell you to add an array to your program, there's only one way to add an array. You put an array in it. There aren't multiple ways to implement an array. An array is just an array. So that all is to say, an array is a data structure. I'm going to give an example that's not on this list, a list. Cool. So a list, without any regard to specific implementation details, is just a collection of things. You could add to it, you can remove it, you can probably look up elements by index, but it doesn't quite describe how you would code it. You can make an object that does all those things using an array. You could use a linked list. You could use other data structures that we're going to talk about later in the course, like binary search trees. But the important thing is that a list is not specific to any specific way of writing code for it. So it's an ADT. And finally, a linked list sort of blurs the lines between ADTs and linked lists in a rather interesting way. And this is actually a perfect segue into the next lecture, if I'm remembering the list of topics correctly. We're going to talk about linked lists and their many variations. In short, though, there are different things you can do, like choosing whether the nodes should be singly or doubly linked, if there should be a link between the last and the first to make a circular linked list, whether you want to use things called dummy nodes to avoid special cases. There are a lot of decisions you can make while creating a linked list. So does that mean that a linked list is an ADT? Not really. The choices that you make while implementing a linked list might have meaningful consequences on how you can use a linked list. Like, a circular linked list will have a structure where every node has a next node, and that wouldn't be true for a non-circular linked list. So those changes that you would make to the linked list implementation wouldn't preserve the sort of contract of a linked list. So rather than thinking of a linked list as a single idea that has many ways you can implement it, I think of linked lists as a specific implementation, like a specific data structure that just has a lot of variations. This will be you on assignment 3. So what are we on now? Lecture 10? Let's get 12 minutes into it. Recall from a couple minutes ago that an abstract data type consists of data and operations on that data, and an ADT is used to hide implementation details, making it so a user of the ADT doesn't have to worry about specific details of how things work, and also the developer can change how those things work without affecting any user's code. Is this the linked list lecture? I think we're going to get into it soon, even if we're not going to get into it immediately. I only prepared for today's lecture, darn. So anyway, a more grounded example of an ADT is a table. This is quite unlike the previous example, the Comp 2140 ADT, in the sense that a table is something that is actually used in practical applications. I can totally see any one of you taking a co-op work term and having one of your tasks on the job being to create a table. Actually, no. On a job, they probably already have their own table implementation already chosen. You will have to make these decisions to do with implementation for more advanced data structures, though. And it's nice to start off with a simple example. So with a table, the contract for this one is that there are entries that you store in the table, and they're accessed by unique keys. A key is sort of like a single thing that represents a entry in the table. If your table is full of students, the keys might be student numbers. If you're storing files, the keys might be file names. If you're storing data about courses at the university, the keys might be the course names, like Comp 2140. Hopefully you can see now that the entries can be much more complicated collections of data, whereas the keys are just a single value that allows you to identify a specific entry. So that was the data part of the ADT. The operations for this ADT are creating a new table, getting the number of entries in the table, adding a new entry, stuff like that. Don't worry about this definition. You'll probably not ever be quizzed on like what are all the operations of a table. No, get out of here. There will be ADTs introduced later in the course whose lists of operations you should know by heart. But this table is just an example. So you've been asked to implement a table. Maybe you're doing that contrived co-op work term situation I talked about earlier. What data structures should you use? So like, you just made a file, table.java, and you're not sure what to put in there. And now I think this is probably getting into the good stuff. The good stuff might not be covered immediately, but we're sort of just starting to touch on the main practical lessons of the course. Implementation choices. Because it turns out all data structures ever made kind of suck, but they suck in specific ways. And what you're going to take away from this course and bring to any company you join is the inability to weigh the pros and cons of different data structures in order to make an informed decision of what to use and minimize the disadvantages of whatever choice you made. So suppose you decided to implement the table using an array. You have several decisions to make from there. Do you store entries in sorted or unsorted order? How would you implement each method? And what are advantages and disadvantages to these? You should definitely think about this on your own, especially comparing them to the linked lists that we'll see soon. But to go over them sort of quickly, I think that insert and search, actually all three of these, would, their implementations would depend on whether the entries are stored in sorted or unsorted order. For a sorted array, insert would probably look up look for where a entry would be placed, basically doing a search, and then insert it at the index that the search finds, moving over any other elements to make space for it. Search would use binary search probably, and delete would also use binary search, and then move everything over. And if it's unsorted, insert would probably just place a new entry at the end of an array, easy. Search and delete would just do a linear search, check every element of the array, and look for the thing that you're trying to search for or delete. And then delete would also have to shift all items over. The asymptotic runtimes of each operation. I'm wondering how much detail I should go into those for. I think I'll provide just a general answer. Binary search would run in logarithmic time. Inserting to the end of an array would take constant time. And then any operation that involves shifting over a bunch of other items would take linear time because it's because for those operations, the worst case is if you delete like the first item in an array, and then you have to shift every single other item to the left. So I think this slide is here to compare and contrast it to a linked list implementation of the table. So I think a decent thing to study between classes is sort of trying to make predictions of how the table would work using a linked list. Recreate my ramblings on the second thing in a bit more detail. Make sure you have an understanding of how the implementation would work for both an unsorted or sorted array. And then think of how a linked list implementation would work differently. So next up, we're going to go over like what linked lists are, and then a bunch of variations of them and how they would impact this table implementation. One more thing before we go. There was a USB-C cable lost in this classroom. Looks like an Apple one. I'm told it was in this corner. I'm probably pointing to the person who lost it right now. So if it's yours, come pick it up after class. That is it, and I'll see you tomorrow.